All right. So we are going to talk about beyond 3G wireless technologies, and this is brand new stuff in the sense that most of this stuff probably happened in the last 2 or 3 years. So listen carefully. And in this lecture we'll talk about generations again. We have already talked about generations before, but I have now updated figure. And then we are going to talk about HSDPA, HSUPA, MBMS, HSPA, and we are moving on to LTE and FemtoCells. All right. In the next generation, the next lecture will be on 4G. So this is 3G plus. All right. So this is the generation diagram which has been updated. And so you already know about that 1G was simply voice network with analog voice, 2G was voice network with digital voice, then 3G is voice plus data. Our 2.5G is also voice plus data, so this is on the way here. And the problem with this data, the 2.5G data, is that it is really data as a voice, which means that we still use circuit switching and everything else. Instead of voice, we send some bits which are data, because we have digital voice, right? In 3G, it is really, basically data as such. And then in 4G, we want it all IP. All IP means even the voice is IP, right? VoIP, right? And so it is really the data network, fully data network. That means all packets switched and all that, right? So on the way to that, we have 3.5G, and this is what we have today, 3.5G. And so we will talk about what is in 3.5G. Now, notice that one addition here is that previously we had only 2 telephony groups, the North American and the Europe, 3GPP and 3GPP2. Now we have a third group, networking industry, which means Cisco, Intel, companies that were generally not counted as telephony companies, right? And they have their own data standard called WiMAX, right? We heard about WiMAX. And it turns out that WiMAX has been officially recognized by ITU as a 3G technology. All right, so I have to show in this picture now WiMAX. And this is very important because in many countries they have spectrums reserved for 3G only. Nobody else can use it. So if WiMAX is not 3G, it cannot use that spectrum. So they worked very hard to get in there, and now in 4G, obviously WiMAX has its own entry. Right, so we'll talk about that in the next class. And while this 3G and 3.5G is going on, so these are the things, HSPA, we talked about LTE and so on and so forth. There was something going on in North American Camp 3GPP2 called UMB for 3G or 3.5G, and that has been disbanded. And they have joined LTE. So that is an example of a Verizon, for example. Anybody who had CDMA 2000, they were going to go, or at least supposed to go to UMB, but everybody is going to LTE. Right? So far the telephony companies are concerned, their future is LTE. The data companies are pushing for WiMAX in the WiMAX next generation, right? And then for 4G, the phone companies are pushing for LTE-Advanced, that is competing with WiMAX 16M. That is called WiMAX 2, by the way. Okay, so this picture is clear. You have seen this picture before, but now it should be clear as to where some of the new things fits in and where we are. So we are right now somewhere here in 3.5G era. There are cell phones you can buy that are HSPA compliant. There are devices that you can buy that have WiMAX, and so on and so forth. Okay, so this line I have shown here, actually this line should have come from edge. That line is misrepresented there. But what it is showing is that the GSM guys have a choice, or at least planned, to go from edge to WCDMA. However, this is a total change. Why it is a total change? Because this is TDMA and this is CDMA. Right? And so many of them, to save money, are going through another path called edge evolution. Right? AT&T is that example. And that is why there is a debate whether edge evolution is 3G or not, because officially WCDMA and CDMA 2000 are 3Gs, so Verizon is saying that you don't have 3G. They have 3G some places, but most of the places they just have edge and the edge evolution. Maybe they just, because it is much easier to go TDMA. This is TDMA, and so it's much cheaper to stay in TDMA zone and increase the speed than to switch the whole thing. And the same thing is going to happen when we go from here to 3.5G, because LTE is OFDMA and all of this is CDMA. So it's not going to be cheap transition. Transition is going to happen, but it's going to take a long time, and some of these things that we're going to talk about today are not reality. These are many of these are promises. Okay, but the point is that because there is a whole technology change, whatever happened before is going to happen now, that people are going to drag for as long as they can. All right, so any question about that? Sorry, any question before I leave that slide? Right, it's clear that this was all analog FDMA, this was all TDMA and CDMA, and this is CDMA, not WiMAX, but everything else is CDMA. And then everybody, the whole world, including all three camps, everybody is moving to one thing which is called OFDMA plus MIMO. So that's another lesson to learn. CDMA's days are numbered. Basically, it's the past generation. The next generation is OFDMA plus MIMO. So let's see more details of the technology that we talked about, and all we have in the next 3 slides is actually the bit rates, the phi, and not that I want you to remember any of this, is just to give you an idea of the ranges of these numbers we are talking about. So CDMA 2000, which is a 3G technology, does 153 kilobits per second. All right, this already shows you how underestimated those numbers are. With 153 kilobits, how many customers can you serve? Then 2000 with 1x EVDO. Actually, this should be called CDMA 1. I'm sorry, yeah, CDMA 1, because it is 1x is CDMA 1. So this is 2G technology. The 2G we didn't have really high-speed data. All we had was a voice channel on which you put data, something like that. So that's why it is so low, kilobits. This went to megabits, 2.4 megabits. This is the first level of 3G. Went to 3.1 megabits and stayed around that range. All right, big jump is here in 3.5G, which actually is not happening anymore. So I should cut that off, UMB. In here, same thing. We are talking about 384 kilobits in 3G, going to 1.8 megabit to 7 megabits, and so on and so forth. Then going to LTE, which is 100 megabit. All right. So the LTE has some hope, basically, in the sense that for you to be able to do some reasonable amount of data transfers, because with 384 kilobits and 1.8 megabits given to 100 users, you're not going to be able to do much, right? And that's where one problem, business problem lies, is that when these guys are making so much money on this 5 kilobit data voice channel, $60 a month, actually I'm paying $160 a month, and this, how are they going to give me 100 megabit or something where they can get million times more money. It's going to be a real business challenge to be able to support data and voice networks. But sooner or later it will happen. So anyway, so to get from 3G to LTE, there are many steps. HSDPA, HSUPA, HSPA plus phase 1, phase 2 and to LTE, right? So we will talk about some of those today. Physical layer. Again, I want to just show you as to how things are moving. So this is CDMA remains CDMA all the way up to once we come to OFDM. So basically OFDM is used for multicasting there in these things, but here OFDM starts with MIMO starts here and the OFDM starts in LTE. MIMO starts even earlier, even with CDMA. Now it turns out CDMA has a problem with MIMO. CDMA cannot do as good MIMO as OFDMA can do. So even though, so basically that was one reason, that's why they could not go higher speed. CDMA has many limitations. Actually, I might have a slide later on which talks about CDMA versus OFDMA as to why CDMA has become the old technology. But MIMO was difficult, but anyway, they put the MIMO here, so with MIMO we can increase the speed little bit without giving up CDMA. But we really get good benefit of MIMO once we come to OFDMA. And I also use the word here SDMA, which I will explain later on, and here it says CDMA TDM. So all the data rates are for FDD. So one thing is, before you compare this with anything else, in WiMAX when we talk about, we don't talk about FDD that much, not right now, but in future we will. Today we talk about TDD in WiMAX, but here we are talking about FDD. All the cellular networks are FDD. FDD means, what does it mean? Frequency division duplexing. So you get some frequency down, some frequency up, exactly the same amount. So you get 20 megahertz down, 20 megahertz up. So when we say 20 megahertz, it's really 40 megahertz. Alright, when I say 100 megabit, it is coming out of 40 megahertz, not 20 megahertz. They are not getting 5 bits per hertz, they are getting 2.5 bits per hertz. Understood? Second thing is, in LTE, they use a special form of OFDMA, which is called DFT spread OFDMA, or also known as single carrier OFDMA, and I will talk more detail about that later on. And now this UMD may utilize, but UMD actually has gone inactive. So there is a problem, because on the Wikipedia it says that UMD has been abandoned, and which I believe, because I have not heard any news about UMD for the last several months, or maybe a year, maybe 1 year. So I went to the 3GPP2 website. However, there is no such thing there in the 3GPP2 website, and they show me a specification dated 2009. So I am not sure. Maybe they are working on a specification which nobody wants to implement. I have no idea. But so far as implementation is concerned, I do not hear anybody implementing it so far. So as far as it is done, this is an active question mark. Data rates depend upon the level of mobility. Now, another thing is that when we talk about these data rates assume stationary objects. These are the best conditions. These are the selling numbers. Okay? So it's like when we tell you Wi-Fi is 55 megabit, if you ever get more than 20 megabits, send me a letter. Because out of 55 megabits, we right away deduct, so much in the collision and so on and so forth, that if you get 20 megabit, you are getting the best performance from Wi-Fi. And I mean AG, not an N. N can probably do better. So similarly, these are the nominal numbers. All right. So evolution of UMTS. So what is UMTS? UMTS is the mobile telephone system. All right. Mobile telephone system means cellular system, right? Universal Mobile Telephone System. This is the official name for 3GPP standard for WCDMA. We call it WCDMA, but they call it UMTS, because WCDMA is more like a technology rather than the name for the thing. Right? It's like if we call WiMAX and OFDMA, that would be kind of confusing. Right? So it has two parts. First part is from the cell phone to the tower, and that is called UMTS access network. UMTS access network, and that is called UTRAN. Actually, I should have switched that one if you want to call that as first part. Maybe first part we should call this one. First part is the back end, and that is the UMTS access network. The second part is the UMTS terrestrial radio access network, UTRAN, which is this part, the radio part. So the R is UTRAN. I might be wrong on that one. I have to just double check. But anyway, there is a two part. There is a radio part and there is a terrestrial part. That's why I am confused, because there is a terrestrial radio here. So this radio part is the one part which is where you use WCDMA, and then there is a terrestrial part which is on the ground, right? Terrestrial means on the ground, which is actually kind of common among many of these. So the standards that they develop, they are called releases, and they release almost every year a new release, or maybe every alternate year or something like that sometimes. These releases first were numbered by the year, so there was a release 99 which came out in 2000, but then after that they said no, that's not good, so let's just number them sequentially. So they have released 4, 5, 6, 7 and 8 which came out on different dates like 2001, 2002, 5, 7 and 8, and each release brings us something new. So the key thing which is new in release 4 is TD SC-DMA. So this one described 3G feature which was WCDMA. This one added a time duplex synchronized CDMA. This is for China, right? Then release 5 added HSDPA. Release 6 added HSUPA. Release 7 added HSPA. Release 8 added LTE and SAE. Okay, so we'll talk about that, all of these, most of these except this TD SC-DMA. Now, I just want to introduce two more terms here. UE is user equipment, which is your cell phone. E and B is the node B. Now, in WiMAX we called it base station, BS. In 3G they call it node B. In 2G they called it BTS. BTS was, I forget, BTS, right? So tower was BTS. Now this tower is called node B in 3G and E and B in LTE. And here they have R and C, which is the radio network or something connection controller, radio network controller, and so that is where the control, most of the control is to go to control the equipment on the tower, right? Alright. So these are the three terms, and this is called, by the way, also called core network, the one that was terrestrial network. So HSDPA is the first thing that came out in 3.5G. HSDPA, we already talked about it in one of these lectures, but I updated this slide and put it here again. And because this is in the right place, now that we are talking about 3.5G. And HSDPA stands for High Speed Downlink Packet Access. So before HSDPA, the data rate were very poor in 3G. So they said, well, what can we do? They said, first thing we can do is fix the downlink. What is the downlink? Where it goes from where to where? Yeah, the downlink goes from base station to the user, right? Base station is on the mountain, so you can think about it. Just imagine downlink. And so that is easy to fix. Why it is easy to fix? Because there is only one transmitter, so there is not complexity. When there are enough n transmitters, there are two difficulties. First, there are n transmitters, so there is collision and things like that and gap. Second thing is they don't have any power, these little transmitters in the hands of the people, as opposed to base station where you can put a power station next to it, right? So it's very easy. So that is the first thing we fix. HSDPA, downlinks. How do you fix it? first of all, we change the spectral efficiency for the downlink. So instead of using whatever code we were using before, we use better codes. If we were using 16 QAM, we can use 64 QAM. If we were using QPSK, we can use 16 QAM. So we get more bits per hertz just that by that method, right? Provided the channel can take it. And so with that, we can get up to 10 megabits in theory, 2 megabits in practice. And we do adaptive modulation and coding. What that means is channel dependent coding. Basically, if the channel is good, we use 64 QAM. If the channel is not good, we use QPSK. Right? So that, by the way, that was not there the case before that, the HSDPA. So if you go to 3G or if you go to 2G, the coding is fixed. And if you remember, what is the coding they use in Edge? You had to write a homework. Remember, in a homework, you had to write a coding for something, a diagram. Those of you who did that homework would remember for the Edge, we had a coding card. For Edge, you had to go and find out the constellation diagram. Nobody did the homework, maybe? 8 PSK. Anyway, I mean, that's just an example. I was just thinking maybe you'll remember that one. But so all these coding were fixed. So whether you are here or there or over there, everybody had the same coding. All right. With HSDPA, they realized that obviously that is not the smartest thing to do. So they have now what we call adaptive modulation coding, and they have higher order modulations. So they have up to 16 QAM, and then as it went on, now up to 64 QAM. Multi-mode. Now this is the thing which needs to be explained. Multi-mode, multiple CDMA channel transmission. So what is a CDMA channel? The way that we do CDMA is that we develop a code, and you get a code, you get a code, you get a code, maybe 16-bit code, that is called 16 chips per bit, right? So if we get a 4-bit code, we get 16 codes, right? So anyway, we get those codes, and then we give one code per user. So then one user can use only one code, only get one channel worth of bandwidth, and only one channel worth of data, and that may not be good. So for data, it is better that we put some number of channels, in this case 15 channels, they combine into one, and now it is shared between the users. So if you need right now, you can use all 15. Later on, you can use all 15. You can use 13 of those, you can use 2 of those. So now we have shared coding, new thing, right? And so that is how they do. So now this looks very similar to the OFDMA. On the x-axis you have time, on the y-axis in OFDMA we used to have what? In OFDMA we used to have 2-dimensional diagram. What was in the y-axis? Second exam was just over 2 weeks ago, and the next exam is next week, next Monday. If you forgot the second exam, you're in big trouble. How do we show in WiMAX when we show 2-dimensional diagrams? What is in the y-axis? Carriers, frequency. Here it is each of the code. Okay, there goes. Okay, so now follow your picture there. No, maybe it is mine. Okay, and I don't know why, but anyway. So these are the codes, their time, and we can give any combination of code and time to any user. Right? Very similar to OFDMA, but it is not orthogonal frequency. It is orthogonal code division multiplex access. They don't call it OCDMA, by the way, but that's what it is. Right? We have orthogonal codes, but a user gets more than one code and more than one slot. This is called TTI. TTI is the transmission time interval, which is 2 milliseconds, and there are 15 channels here. There are actually 16 channels. One of them is used for control or something. So 15 are used for data. So 15 are assigned for HSDPA, and they are shared among many users, and then extension to WCDMA, which uses dedicated user channels. The rest of WCDMA uses dedicated channel. You get one code and you use it. Whether you use it or not, it's yours. That is dedicated, right? With this one, it is shared. If you don't use it, somebody else will get it, right? So this is So previously, as you can see, WCDMA was designed more for voice, whether you speak or not, you need the channel because you're really listening when you're not speaking. Yeah, go ahead.
But let's say if we have the same code, right, and let's see this time slot I don't use it, but in the next slot I'm going to use it and you also going to use it, then they collision.
Yeah, no. So basically this is by request and grant. This is very similar to WiMAX, where the subscriber says that I need to send 300 bytes. And then the station says that this is your slot.
You mean per frame, like
per frame.
You have to share this allocation.
That's why that last channel is there. So there is one channel which is basically used for allocation map. Everybody understood that question and the answer? Is that clear? What Chakshay asked? David? He asked as to how we know where to use it. Basically, first you tell the base station that I need so many bytes to be sent, so it calculates how many slots you need there, and then it tells you which slot you can use. You can use channel 5, 3 and 2, time number 1, 3 and 5, whatever. Right? So there's no collision. Yeah. Yeah.
OFDMA plus the CDMA something. So we have the frequency and time, but we also in each sub-channel we do a share code or something.
Yeah. What we are saying is, can we do OFDMA with CDMA? Yes. And that is called multi-carrier CDMA, where each subcarrier has CDMA on the top of it. Yeah, that is done. Actually, in that case, generally, because each carrier is so little, 10 kilohertz, that you don't really, you might have bigger carriers, then you won't use little carriers, and you probably have something like that. But all combinations are possible, yes. All right. So everything on this slide is clear, right? Then we move on to the HSDPA. Okay, so the next thing is they also use HARQ, hybrid ARQ. Now all of this was covered in WiMAX, and I will ask again in final exam. So this is the kind of thing where you say, well, I didn't read WiMAX, but here I'm not going to explain what is HARQ because we already explained what is hybrid ARQ. If you forget hybrid ARQ, if you forget OFDMA and all that, then basically all of that will come back here. So what is hybrid ARQ? Anybody knows? Automatic request, repeat request. That is correct, but what is hybrid about it? Nobody remembers. Everybody remembers? Anybody remembers ARQ? What is ARQ? ARQ is automatic retransmission. Basically is that if the packet is not acknowledged, then you retransmit it. That is ARQ. And generally the word ARQ is used at the data link layer and not at the TCP layer. So in the TCP layer we call it retransmission, right? So at the data link layer we call it ARQ. However, when we do it at the physical layer, we call it HARQ. So how do we do at the physical layer? Well, the acknowledgement comes back at the ACK layer and at the MAC layer, and the layer says, well, it is bad. Then instead of sending the same packet again, we send another coding. With another coding, we send it. Maybe the coding would be incremental, could be a repeat, or could be a different number of FCC or something like that. So with a different coding, we send it so that the previous one plus this one is combined by the physical layer and then decoded. So that's why it is hybrid. Hybrid means it is two layers, physical and the MAC combined. Generally the ARQ is just MAC layer. HARQ is combined, hybrid. Alright. Third thing they did was, a final thing, I don't know how many things that we have talked about so far, is that they moved the scheduling to node B. Why? Because previously node B was dumb and if you have to decide when to transmit, what to transmit, you have to go to RNC, which was somewhere miles away. And if you want to do HARQ and you want to do this dynamic scheduling like this, right, you need to be near the action, right? So that means that we don't have to go to RNC for all of this. Such decisions are made right at the node B. What is node B? Base station. All right. So the radio network controller is far away, and we don't go there. Okay. So this is HSDPA. Any question about HSDPA? Clear? So then we can do something similar with HSUPA. UPA is uplink, high speed uplink packet access. However, it is difficult. Why it is difficult? Because there are multiple transmitters, and if we let multiple transmitter transmit, and let's say C is speaking and C is speaking very softly, and you are speaking very loudly, when you speak, my ears get tuned to your level. When C speaks, I can't hear it. That same thing happens to antenna. If they receive some high level signal and then they receive some low level signal, they can't hear it. Right? And in fact, if they speak at the same time and one is speaking on frequency 1 or code 1 and another one is speaking on code 2, you can just imagine what will happen. One is speaking code 1. Code is like languages, right? So one is speaking in Chinese, one is speaking in English, and Chinese is very loud, or English is very low, or something, combination you can think about. Very difficult to do that. So what is required is power control. Power control means everybody's level has to be set so that all is speaking at the same level. Right? So what we have to do is we have to listen to the user's level and say, look, you have to increase your level by a factor of 4. You have to reduce your factor by a factor of 2. So there is a feedback. Right? The transmitter has to tell the receiver has to tell the transmitter that please reduce your power. That means the base station has to tell this mobile, please, you are very close to me, my ears are getting turned apart. So that is required. A scheduler in node B, but data in UE. Now there is another problem. That now the scheduler is not where the data is. We moved the downlink scheduler from RNC to ENB, but uplink, the scheduler is still in the base station, but the data is in the mobile, so there is one feedback loop there too. The mobile has to tell the base station that I have so much data, then the base station schedules it, and then you send it. Third thing is, a single user cannot utilize all codes, so parallel transmission in each TTI. So basically, previously there was only one transmitter, 15 codes, and all 15s were used by the base station. Right? Here, now we have to distribute it. And then HARQ has to be, again, same thing, we have to implement HARQ if we want to implement. By the way, it's just called fast HARQ, but basically it's the same thing. Now we have to make it more smart. This was not there before. So it's just UPA was done in some release, as we saw. That was release 6 in 2005. Right? And then they were combined together to form HSPA. But before I go to HSPA, I must also want to talk about MBMS. So after HSUPA, they also had a new feature called MBMS. MBMS is Multimedia Broadcast Multimedia Services. Actually, that is wrong. Multicast Services. Right? Broadcast multicast services. So a good example is mobile TV. So it's not worth sending a mobile TV to 5 users if 5 people are watching the same TV. Right? So they said, well, why don't we just introduce this concept of multicast and broadcast first time? Right? Now if you do multicast broadcast, then the question is, shouldn't we synchronize all of the towers as well? So basically that is what is done, is that if you do broadcast, all the towers will be sending, they will reserve a particular time, they will synchronize, and they say, okay, at 1 minute after, or 1 millisecond after, this time, I will start my multicast, you will start multicast, same program, same time. Alright, so the program goes to all the towers, is broadcasted, and everybody receives it. That is broadcast. But if you want to do multicast, then you have to be a little bit more complicated, in which case you have to find out if you have a user in your range where the user is, and whether you can just broadcast to that user. In some cases it might be just good enough to just do unicast rather than multicast, or do, if there were 2 users are here, both of them are here, then you just direct to that side rather than do everywhere. So all that comes in with the multicast. So node B tracks the users and directs the signals accordingly, and could even be unicast if there is only one user. So everybody understand that? Multicast broadcast. This is a new mode. Before, actually everything was unicast, right? Everybody has a channel and dedicated channel and so on and so forth. So all of this is combined, is called HSPA, and with HSPA you can get up to 64 QAM in the downlink, 16 QAM in the uplink in release 7, and release 8, which is the latest release. Actually, I think release 9 is probably out now. But release 8 allows 64 QAM and MIMO in the downlink. So now MIMO has been added here in release 8. Alright. So much about HS business, right? High speed. Any question about any of this before I move to LTE? Alright, so LTE stands for long-term evolution. And basically they have added the word E in front of everything. So EMTS is called EUMTS, evolution of UMTS. It has 2 parts, E ultra plus E utron. E ultra is the radio part, and E utron is the terrestrial part. Right? That T is for terrestrial. Well, kind of confusing to me. But anyway, so LTE is the replacement for WCDMA, basically the wireless, the radio part. Right? And they are also changing the core network. The core network was whatever it was before, and I have a better picture later on, is now being replaced with what they call SAE. Actually, the name SAE has been replaced as well, and it is called EPC. EPC is Evolved Packet Core. Evolved Packet Core, which is all IP packet core. Its original name was SAE. Okay, and in this case, all IP packet core, as I said, means that even voice is IP. So there is no analog voice, there is no circuit switched voice. Okay, makes sense so far? This is designed for trial and deployment in 2010, which is this year, and I would really be surprised if we see deployments in 2010. I think trials probably will begin in 2010. There is no equipment. The standards just came out. They have to go through what they call conformance things, like WiMAX forum does conformance rules first. Multiple vendors get tested, and then you can do deployments. But this is what it was designed for. Frequency domain equalization, which is OFDMA. So, and there are 4 things which are quote new in LTE, and I say quote new because they're all there in WiMAX. And actually all the companies that worked on WiMAX are working on LTE, because what happened now is there are 2 camps. the data camp and the telephone camp. The data camp is the one that designed WiMAX. They go to IEEE, right? That is where the Ethernet was designed and so on and so forth. And Wi-Fi was designed. The telephony camp doesn't go there. They go to ITU. They go to 3GPP. So they designed LTE. And obviously there's the same company, same experts, same people. So, you can see 99% overlap, except there are few things which are different. Clearly what is different is that it is designed for telephony network. So anywhere there is any conflict, telephony people just make a decision in favor of their current technology, current business, compatibility and so on and so forth. Now there is no compatibility as such, as you will see. It's as compatible as IPv4 is to IPv6. That means dual mode. The phones right now are 4 mode, there will be 5 mode. But that's at least compatible that way. So, so one thing, so there are 4 things and I wrote them 4 here because number 1, 2, 3, 4, because this is what is the latest in wireless networking. And this is what is happening in all of the technologies that are being developed today, whether it is WiMAX or whether it is LTE. First thing is what we call OFDMA. The technical name for that is frequency domain equalization. The word equalization comes in the fact that if you have multiple transmitters, we said we have to equalize the volume, we have to equalize this and that. You can do that in time domain, you can do that in frequency domain. The way we do it in frequency domain is by doing this fast Fourier transform, and that is what we call OFDMA. Alright? So that was not there before, and so we had tough time doing equalization, and because of that we could not use big bandwidth. Like maximum that they could use in CDMA was 5 megahertz. With 5 megahertz you cannot go to 100 megabits. Right? So if you want to go to any high speed data, you really need to do this wide channels, and for that you need OFDMA, so everybody is going to OFDMA. Second thing we do is MIMO, and I will talk about a little bit more about MIMO in this lecture. Third thing is channel dependent scheduling. I already talked about that. Can anybody explain what is channel dependent scheduling? Can you guess? No? Yes. So based upon the currently available, if it is raining, it's a different code than if it is not raining. If it is far away, it's a different code than if it is near. So that is what HSDPA did. That is what WiMAX did. That is what LTE does, right? And that is what everything else does. Dynamic channel allocation. So previously we had static channel allocation. So when you got on the phone, they gave you channel number 15 and that's yours forever. Right? You got a code number 15, that is yours forever. With dynamic means it is for this frame. Next frame you will get another thing. So so basically we are sharing almost everything. Dynamic channel allocation. Okay. So that is LTE. So here's the thing. If I was giving a lecture on LTE, I would talk everything that I had talked in WiMAX because most of this thing is overlapping. I'm just going to talk about 1 or 2 items here because we have already talked about WiMAX, right? So let's first talk about the goals. It is designed, now these are the goals, not that you will get in the equipment because equipment is not here yet and these are all the nominal numbers. So these are the best numbers basically as calculated on paper. You get 100 megabits using 64 comms ISO on 20 megahertz, which is actually 40 megahertz. So I have to do 20 times 2 megahertz. And 326.4 megabits using 4x4 MIMO. Okay. Uplink rates of 50 to 80 megabits using SISO. Everybody knows what is SISO? If you don't, then how come you didn't ask? Now it is written next to MIMO. So what is MIMO? What is SISO? Everybody knows what is MIMO? Okay, so what could be SISO? Right, single antenna. So, scalable channel bandwidth. So that's another thing is previously the channel width were fixed. So if you had WCDMA, you had 5 megahertz, you couldn't have 3 megahertz, you couldn't have 7 megahertz. Right? Now they are going to use whatever they can get from 1.4 to 3 to 5 to 10 to 20. But you need times 2. And you can actually do times 1 too because it does TDD as well. Multiple frequency bands. Whatever band you get, 700, 900, 1800, just like WiMAX. Sub 5 millisecond latency for IP packet. Now, this is distinguishing factor. Why distinguishing? Because one of the reasons they asked us, why do you need LTE? Why not just WiMAX? They said WiMAX is not fast enough in latency, and the reason it is not fast enough in latency, suppose you get a packet. You have to tell the base station that I got a packet. That will take how long? The WiMAX frame is 5 millisecond long. They repeat every 5 millisecond, downlink, uplink, downlink, uplink, downlink, uplink, right? So first you have to find an uplink to tell the base station, which is 5 millisecond, and the base station tells you that, okay, you got the slot number 3, then you send the data, so there are already 3 trips, right? 15 milliseconds before the data made it there, right? That's too long. So what they did here is, they did the frame which are 2 millisecond long. Right? So now you can do that in 3 round trips is, 1 millisecond, you tell it, and next millisecond you come down or something like so each, something like that. So basically this is less than 5 milliseconds, so this is one reason. Second thing is and so there is one more related. So this is one major difference, right? It's not really major as such because all you did was the 2 millisecond frame is allowed by WiMAX, except that it is allowed by 802.16 but not really standardized in WiMAX. WiMAX group set 5 millisecond. So anyway, then the distance mobility wise, this is optimized for 0 to 15 kilometers, high performance up to 120 kilometers, and it will just work barely at up to 350 kilometers. After 350 kilometers, the performance is not guaranteed, working is not guaranteed. So can anybody guess as to what happens at high speed, what goes wrong? What happens at high speed? Doppler effect. And what does Doppler do to OFDMA? Each carrier frequency changes. Basically, you have the carrier here, and if you are moving, the carrier looks like over here, right? So it can overlap the other carrier, right? So there is inter-carrier interference. Compatibility with other cellular networks using multi-mode devices. Now this is all compatible with other 2G, 1G, 3G because your phone will have 1G, 2G, 3G in it. Yeah.
So that means that the cyclic prefix should be statically changed based on the speed.
Okay. So he is asking a very advanced question. He is asking, shouldn't the cyclic prefix be changed depending upon the speed? Right? What is cyclic prefix? I need another slide to explain this thing, but let me just say basically cyclic prefix has nothing to do with the mobility. What is cyclic prefix has to do with the reflections, multipath. So what happens is if something went there and came back to me and something went very far away and came back to me, they come at different times. So there is what we call inter-symbol interference. If I had a bit which was so long, the second bit was here, but the first bit will overlap the second bit. So that is ISI, as opposed to what I just said was inter-carrier interference. So inter-symbol interference happens because of multipath, right? Because of multipath, there is different delays, and therefore we have symbols run into other symbols. Right? Now, to overcome that, what we do is we make every symbol longer. So what we do is, instead of having a symbol which was 1 microsecond long, we make it 1.2 microsecond long, and 0.2 microsecond at the beginning is same as the 0.2 microsecond at the end. That is called cyclic prefix. Because what we have done is we have taken the end, the tail, and put it in the front. So if there is any overlap, if somebody runs over it, no big deal, I still have another copy. Right? So cyclic prefix fixes multipath, and that is fixed, by the way. So that is not adaptively changed in any of the technologies so far, because that is one of the fundamental parameters. Just like we don't adaptively change the intercarrier spacing. So for example, in WiMAX the intercarrier spacing is 10 kilohertz. In LTE it is 15 kilohertz. That is not changed. Even so, basically we keep that fixed universally. So whether you use 1.4, 3 megahertz or whatever channel, this intercarrier spacing is 15 megahertz fixed. Right? Similarly, the cyclic prefix is fixed.
Then what is technique to try to mitigate these OFDMA?
Yeah, right. The only is 15 megahertz, or 15 kilohertz. So basically, WiMAX 10 kilohertz will allow you to have only so much error in your frequency spacing. Right? With 15 megahertz, now the carriers are a little bit farther away, so you have more room to move around.
But there is no such way to do something, to fix something to support this. For example, when we are at the low speed, we get some number, right?
Yeah.
So, and when we are in the high speed, we get some number. So what makes it different?
No. Sitting
we can use
at high speed, what will happen is you will have Doppler, you will have intercarrier interference, and then what will happen is your data error rate would be higher, and so your effective rate would be very low, to the point where it will become zero if you are running at 350 kilometers per hour, and then sorry, your error rate is 99%. I mean, it's not that 15 kilohertz means there is no interference. There is interference even with that spacing, but there is less. If it was 10 kilohertz, there will be more interference.
Is it possible to maybe change the intercarrier spacing if we are in that low speed? We can just.
That's what I said. This is one of the fundamental parameters. So it is not changed dynamically. Not right now. Maybe next year. Okay. I mean, right now it is just too complicated to make devices that have. So just like I said, cyclic prefix is not changed, carrier spacing is not fixed. So there is a whole set of parameter values that we specify in our WiMAX papers, remember? Those are basic parameters, we don't change them. Even, for example, the frame size is variable, right? I mean, why don't we change the frame size? Not in 16E, but in 16M, yes. So maybe the next version may have it variable, but not in this version. So by the way, 16M, when we talk about next time, you will see that they have changed, that they have taken care of many of these issues, because these are the same people. They go there and then they come back here and they say, wait a minute, we need to change it here. So they are just following each other. All right. So CDMA versus OFDMA. CDMA versus OFDMA, I think we have discussed most of it, but just want to be one more time repeat it. If you want to be frequency selective, means that that there is a noise which is in this zone, and you want to take care of it. It is much easier to do with OFDMA. It is not possible to do with CDMA, because even that one frequency, if you have 5 megahertz channel and you are using the whole 5 megahertz in CDMA, the frequency selective effect noise will affect you. So there is no solution. Symbol period. The bits are very short. Actually, the bits are shorter than the bits itself, the chips, because instead of bits we transmit chips in CDMA. So there is a lot more symbol interference. Well, it's not symbol interference, it is chips interference. Symbol is that big, by the way. Each bit is a symbol, right? So, or it could be even more. So the symbols are short. Here the symbols are very long because we have only 10 kilohertz. So that's the advantage of having 10 kilohertz. 10 kilohertz symbols are so big. 15 kilohertz symbols are smaller. All right. As you increase the width, the symbols become smaller, and that's the whole purpose of OFDMA. The OFDMA the basic principle is that we don't want to use this much bandwidth, we want to use only this much. With this much bandwidth, the symbols are so big. Each bit takes longer. And that's the whole idea of OFDMA. So there is a trade-off between 10 and 15 kilohertz, and the trade-off is mobility versus multipath. Big symbols are good for multipath, but small carrier interspacing is bad for high speed. You see, so either you go high speed or you go multipath. One of the two. And so that's the kind of trade-off we have to make. Equalization. This is equalization works only up to 65 megahertz, and this is for any bandwidth. So now we are talking about 100 megahertz. Okay, very very wide channels. Resistance to multipath. This is very difficult to do with CDMA, and this is possible to do with proper cyclic prefix. This is what we were talking about. The cyclic prefix is that repeated part. MIMO is very difficult to do with CDMA. It's very easy with OFDMA. Frequency distortion is averaged. This causes intercarrier interference. So that is what the problem actually is with respect to motion. OFDMA is not good for motion. Okay. Then user multiplexing you can do by having orthogonal codes. Here you can do in frequency and time. Alright, so with that we know why CDMA is going away, why OFDMA is coming in. Now there is a second change that the LTE people have done, which is not in WiMAX, is single carrier FDMA, SC-FDMA. SC-FDMA. And the reason they have to do that is because OFDM, each carrier is modulated according to specific channel conditions. So you have these 1,000 subcarriers. One has BPSK and one has COM64, right, depending upon the condition of that particular carrier. Because of that, there is a big variance between the minimum and the maximum. There is a big difference between the peak and the average power, and that makes the amplifier design very difficult. I think we talked about this earlier, right? Peak to average power ratio, if you get an amplifier, they are, by the way, the most expensive part in the whole system. So when you design a UE or a base station and you get the power list, part list, and you get the cost list, the highest cost is amplifier. And I have done that because at some point I was trying to design some product. So highest cost is amplifier, and if you use, so according to them, if you use this high pepper thing, then it will be even more expensive because the amplifier has to operate linearly in this range as opposed to in this range, right? So how do we reduce the pepper? We use single carrier. With single carrier, the peak to average is very small because single carrier, right? So how do we do single carrier? Basically, what we do is we take the symbols that we want to translate. So these are in time domain. We send through a what we call discrete Fourier transform chip, which is M by M. That comes out in the frequency domain as M frequencies, M carriers, M subcarriers, right? This is discrete Fourier transform. What does Fourier transform do? Translate from time to frequency or frequency to time, right? So it comes out M. Then we do a inverse discrete Fourier transform, which is N by N, and we connect these M to some M symbol. It doesn't have to be any middle M or anything like that. This could be any M values out of N, right? That comes out in time domain again now. So this was in frequency time, this is in frequency domain in the middle here. See, it says subcarriers, right? Now after inverse it becomes time domain again. Now we do all that cyclic prefix and whatever we need to do, and depending upon where we connect this spectrum will be either here or in the middle or something like that, depending upon where you connect these pins. Alright. Now, so this actually, when you see here, this looks like a single carrier because this whole carrier, this is totally used. But the way we got this single carrier is by doing a Fourier transform and inverse Fourier transform. Right? Now if you didn't have single carrier, then all we do is we take this and we convert into a n by n discrete Fourier transform, right, for OFDMA, and we connect all of the pins to all of the pins. Right? In that case, you get the subcarriers here, and then you get this kind of. So basically, so the idea is that instead of having this full DFT, we have a small DFT. So this is called DFT pre-coded OFDM. This is called DFT pre-coded OFDM, because before we went to the OFDM part, we had DFT pre-coded, right? So M by M DFT is used before M by N IDFT, where M is much less than N, and results in a waveform that is similar to a single carrier, and therefore it has 1 to 2 dB less pepper. So when you talk to WiMAX guys, they say, hey, there's no difference, man. Come on, 1 to 2 dB for which, why we have to make such a big deal about it? But when you talk to LTE, oh, that makes a big difference. That's the key. Okay? So that's the debate going on right now. Whether this change is worthwhile or not. Why don't we just take the WiMAX standard and take the chips and start making it for cell phone companies? But they say no, this single carrier makes a big difference. That frame size of 2 milliseconds makes a big difference. But those are the two major differences. Okay, so much about that. Now MIMO. So MIMO, I just wanted to add some more information about MIMO before you get out of this wireless class. And so you already know SISO was single antenna, right? And MIMO is multiple antenna, both sides. So this is single user MIMO. Why is it called single user MIMO? Because each user has to have multiple antennas. So how do you put 2 antennas on a tiny cell phone? And they have to be by the way quarter wavelength or half wavelength apart. And if the wavelength is 700 megahertz, the wavelength is so big, you need to carry a kind of an antenna with you, like an umbrella or something. So that doesn't work, right? So then they invented what we call multi-user MIMO, where you need 2 antennas, but they don't have to be on the same equipment. They could be on 2 different users. And the way it works actually is, because the way it worked in the previous single antenna was that we had this matrix, carrier versus time. These are subcarriers. Here I've shown 4 subcarriers and 4 symbols times. And we use some of these combinations for pilot. These are the reference symbols, where we figure out if I'm sending you this here, what you are getting, whether the channel is good or bad. So we put the pilots, right? From the pilot we can tell the condition of the channel, right? So these pilot positions tell us, when you have MIMO, then the pilot positions tell us which of the signal is which path, following which path, and we can actually get a very good idea of what we call the channel matrix using these pilot symbols. Same thing happens here. Now when we are sending these to these, we tell one user to put the pilots here, XX, and put other user to put the pilot YY. When we receive, we can get a good idea of the channel matrix, and we can separate out the 2 users. And so that is called multi-user MIMO. Multi-user MIMO means user only has 1 antenna, but there are multiple of the users, therefore they have multiple antennas. Okay, everybody understand multi-user MIMO? All right. Then there is called cooperative MIMO. Cooperative MIMO is doing the same thing, but doing on the tower side. Instead of having 1 tower have 2 antenna, which is much easier to do. It's no big deal to put an umbrella on a tower. But if you use 2 towers to transmit, then you got a cooperative MIMO. These 2 towers are collaborating to reach you. Right? So this is another kind of MIMO. All of these modes are allowed in LTE. And if they are allowed in LTE, they are also allowed in 16M. They may not be allowed in 16E, but they are allowed in 16M because 16M came after LTE. So this is the thing. First came 16E, then came LTE, then came 16M, and then coming LTE-Advanced. All right, LTE version 2. So the LTE version 2 will have everything that is 16M plus more. So there is a repetition of all of these things, and this is a nice debate in the industry. I will stop right here. Maybe, I don't know, maybe I should not stop here. I should finish 2 more, and then that will be a good point to stop. So this is basically, this slide simply shows the complete description of the 3.5G. So you have 2G systems which have the BTS and BSC and then MSC and gateway and all that, and this is all circuit switched. CS core means circuit switched core. By the way, this slide goes with the next slide, which has all the acronyms. And then when we had 3G, in 3G we added the packet switched core as well as circuit switched core. The voice went through the circuit switch, the data went through the packet switched part. Now in 3.5G and 4G, first of all, this RNC is gone. So we have E and B, which does the whole thing. And second thing is that everything is packet. This is called Evolved Packet Core, EPC, Evolved Packet Core. This whole thing is called Evolved Packet System, EPS. All right. So that's all I wanted to say. So basically, so the idea is that we have finished now all about 3.5G, almost. And next time when we come back, we will talk about FemtoCells and 4G.